Hi everyone, good afternoon. So today we are going to touch upon a very interesting topic, and it's an emerging topic in the field of machine learning and AI. Um, so as we are going more and more into AI-driven world, so it's very good to understand how the AI system works. So what are the inner working of different algorithms? How a machine learning model or an artificial intelligence system takes a particular decision. So we have heard recently that there are multiple researches that are going on in Google where an algorithm or a robot can actually interact with human with emotion and all. So it is very interesting, but at the same time it can be very scary. And when it actually takes decisions in case of businesses or in case of on in our personal lives, it is very important to understand how it is taking their decisions, and based on which we can basically take action upon that. So that is our topic for today. So we will mainly focus on the importance, application, and the advancement of explainable AI in the field of artificial intelligence and machine learning. Next slide, please. Okay. So as I was talking, so currently, if you look around, you can see artificial intelligence everywhere. So starting from when we wake up in the morning, we look at our mobile, we check our emails, we check our messages. From there, the decisions driven by artificial intelligence starts, and from there, whatever we do, whatever we buy, if we go to e-commerce site, we buy something, we look at the recommendations, we go to Netflix, we watch movies, we look at different recommendation things. From there, multiple things that are going on around us. You see multiple decisions that is being driven through AI, artificial intelligence. So it will not be it will not be over exaggeration of if I say that we are currently living in a world of artificial intelligence. So, Aditya, next slide, please. Okay. So, currently, although we are living in the world of artificial intelligence, we hardly understand, even we modelers hardly understand how the artificial intelligence takes a particular decision. So, sometimes it's the lack of the algorithm, that knowledge about the algorithm. Sometimes it's the non-linearity of the algorithm, which makes it very difficult for human to understand who is going I'm sorry how the AI system is taking the decision. So the lack of the explainability of a particular model leads to lack of trust, and it hampers our ability to trust the AI system. Uh, I'm not sure, but I'm sorry, is it possible to remove these pop-ups whenever somebody is joining? Because it's actually coming in between the screen and I cannot see the screen actually properly.
Kushal, can you see now? But I think the bottom right component will still be.
Uh, so I can see whenever somebody is joining or waiting in the lobby, I can see actually, and it's coming right in middle of the slide.
Yeah, yeah. I'm not sure how to remove it. Okay, much better now, right?
Just still coming actually. Just a second. Yeah, I think now it should be fine. Now it should be fine. Uh, thanks, Aditya. Yes, so what I was saying is it's extremely important to understand how artificial intelligence takes a particular decision. And we humans sometimes find it very difficult to understand that decision making process. And if we do not understand how the artificial intelligence is taking certain decisions, what will happen is we will not have enough trust. Our stakeholders will not have enough trust on that AI system. And if the stakeholder or a human do not have enough trust on that AI system, that AI system will not be implemented for decision in business or for taking decision in any angle or any aspect of life. It can also lead to data security, privacy, or ethical regulations. We'll discuss all those things in detail in some time. Also, if we do not understand uh, the decision making process of the AI, then it will not be able to regulate the biases that is that will come with the decisions taken by AI system on the input data. So, Aditya, can you go to the next slide, please? Okay. Now, machine learning and AI has been there for a very long time, and it's being evolved. It's evolving for a long time. And as we evolved throughout the history in machine learning models, we focused more and more on the accuracy. So we first started with say a very linear model, for example, linear regression. From there, we started getting into nonlinear models like say boosting model or bagging model, and then gradually we got into neural networks and different kinds of ensemble models as well. But while we focused on accuracy, we lost the explainability part of it. If I look at a neural network model, we hardly understand how the neural network model actually is taking the decision. If a neural network model is saying or classifying a cat as a cat and a dog as a dog, we do not know on what basis or which part of that image the neural network is focusing on to say that this picture is of a cat or this picture is of a dog. So we have come a long way. We have built a very complicated model in order to gain a lot of accuracy, but at the same time, we have lost the explainability part of it. We do not know how these models, these advanced and complex models, are taking multiple decisions. So the graph on the right bottom side, if you look at, so you can clearly see that more complex models, less is the explainability, although we can have much higher accuracy in terms of its predictive power. So, however, now we want to have both. We do not want to compromise on the accuracy, because that's kind of bread and butter of any machine learning model. Without having enough accuracy, that model will be very difficult to deploy in any whether it's a business setup, whether it's an academic setup, or whether it's a any other setup where machine learning models or artificial intelligence models are being deployed. But at the same time, like I told before, explainability is also an important aspect which we need to focus on. Can I go to the next slide? So, like Sundar Pichai once mentioned, it's not enough to know if a model works. We need to know how it works, because the how part is more important in order to understand the AI's inner working and have transparency and have more trust on it. Next slide, please. Okay, so let's have a look at the more formal definition of explainable AI. So explainable AI is an emerging field. It's a relatively new field in the machine learning domain, and it primarily aims to address how black box models takes decisions, how AI systems are are working the way they are working. And this area mainly tries to understand the different steps and the models that are involved to make those decisions. So we will mainly focus on explainable AI is a bigger part. So we will mainly focus on how machine learning models can be explained or how interpretable machine learning models can be made. Next slide, please. Okay. So the movement, initiatives, and the efforts made to make the artificial intelligence model more transparent, to have more trust on those artificial intelligence models. We have the explainable AI methods are majorly used, and to produce more explainable models while maintaining a high level of learning performance. So, which means that we do not, like I told before, we do not want to lose out on the prediction accuracy, but at the same time we want to understand how the models are making decisions. So that is where the explainable AI or XAI in short comes into picture. Next slide please. Okay, so these are the various reasons why uh, explainable AI system is important. I have already spoken about some of them before, but first one is to explain to justify. So we have, suppose, for example, let's take a situation or a scenario. Say I have given a bank loan. A bank has given a loan to a customer. Okay, and or rather, the customer has applied for a loan, and bank has rather rejected that loan. It's not enough to tell the customer that his loan request has been rejected. We also, a lot of time, we also need to give, or the bank also need to give the reason why the loan has been rejected. We cannot say that, okay, based on a neural network model, your application has been rejected. So we have to tell them that, okay, maybe your salary is not enough, or you are not eligible because of your age. So those kind of specific reasons we need to give to the customers. We need to justify a decision based on real life situations, and that is one of the reason why explainable AI is important in real life. We need to justify, we need to explain. The next one is to explain to control. So if I do not know how a system works, I do not have any control on that system. It can go haywire. It can take decision on its own, which I do not even understand. So if we want to have more control on the artificial intelligence or a robotic decision making process, it is very important to understand the model's decision making process so that we can control that decision, and if required we can change those decisions. The next one is to improve. If I want if we want to improve a model's decision making power, or if I want to improve the even the accuracy, okay, I want to first understand how it works. Only then I can work on top of that in order to improve that model's working. And finally, obviously, if I do not know something, I cannot.
Hello.
Sorry, sir. It's audible, sir.
I think
Okay,
Kushal.
yeah, sorry. So you can hear me right now?
Yeah, we can hear you, Kushal.
Okay. So that is when you can actually go on and discover something. So these are four major pillars or major reasons why explainable AI should be adopted more and more in a business or academic setup. Next slide, please. So this is kind of an architecture where we can see that where basically the explainable AI comes into picture in a typical machine learning algorithm or machine learning setup in any organization. So if you look at the top left corner, we have the data collection, and which basically goes into the explainability method for the data. And then on the bottom left corner, you can see the machine learning models, which is getting into the explainability methods for machine learning. And both of these, from the first one, for the explainability method for data, we can get the data insights. And from the explainability method for machine learning, we can get the feature analysis. Feature is nothing but different variables, different reasons, like I told, age. for the banking example, bank loan example, or it can be the salary in that case. So those are basically features. So which feature is more important? The which feature, the specific threshold of particular feature. So say age greater than 60 is not eligible for a student loan, for example, I'm saying. So those kind of feature analysis will come from the explainability method for machine learning. Both of them together from the data and the model will get into explanations, and that explanation will basically help our stakeholders to ultimately take the controlled and human involved but artificial intelligence driven decisions, which is the green part in this entire case. And suppose we do not want any human intervention, even then on the right side great part, you can see the explanatory method for machine reasoning. So basically we also need to have machine to machine explainability. So even if we do not want any human intervention, we should have some explainability in place, so that like I told, so that there is a transparency, so there is a trust, there is a controlled decision making process through the artificial intelligence setup. Next slide, please. Okay, so now let's have a look at what are the different things that helps human to build a trustable AI system. So on the left hand side, you can see the interpretable machine learning, which basically goes into that pyramid structure. The first one is the fairness. So if again, let's take that bank loan example. Suppose a customer comes, requests for a loan, okay, and the AI system rejects that loan application. We need to know whether that loan application is rejected based on caste, based on religion, based on ethnicity or not. If it is, then it is against say equal right for all the citizens, or it is against maybe certain law for that particular country, or it can be against the culture of that country, where we want to include diverse people from diverse cultural and ethnic background. So fairness is very important for most of the countries, and that is when, even if AI is taking a decision, we need to understand on what basis it is taking certain decision, and then we can act upon that. Let's come to the middle part. So privacy, security, safety, robustness, reliability, all these are extremely important. We have all heard many times the data security issues. Data gets leaked, data gets hacked, okay? Privacy issue, data privacy or model privacy. So we have all heard about the 2016-17, what happened with Facebook and Cambridge Analytica, all those things. Okay, so whether a machine learning model is using certain data which it is not supposed to use, okay, or whether it is actually breaching customers or citizens private data or not. So those things we need to understand. If I have a database, I have a machine learning model, I do not understand what is happening inside that, and then I'm just consuming the decision taken by that machine learning model, it may lead to a huge security and privacy issue. So it is absolutely no situation. So we have to understand, we have to be accountable for our artificial intelligence models, and in order to do that, we definitely have to have an interpretable machine learning setup in place. And finally, the bottom part of it is the trust. If we do not have transparency, we do not have any trust on that model. So interpretability leads to transparency. If our customer knows how a system takes a certain decision, how the machine learning model or artificial intelligence system is impacting their life, or certain decisions that they're taking on a daily basis, only then they can have trust on that system. If they do not have trust, they will stop using. When I say customer, I'm also including our stakeholders, business as well, or in case of academic setup, it can be researcher as well. If the transparency is not there for a particular decision making process, no one is going to utilize that. So transparency is the and trust is the very base of utilizing any system, not only machine learning model or artificial intelligence, rather any system. And if we want to have transparency and trust for machine learning model setup, we have to have interpretable machine learning model in place. Next slide, please. So this is, as I told, this is like a very emerging field. It's a very new field. Machine learning is a very old concept, or data science, machine learning, statistics is an old concept. But as from 2010 onwards, we started using very complex models. We have seen the boom of, like I told, ensemble methods, neural networks, and all those things, CNN, RNN, LSTMs. We have we felt the need of the explainable AI, and you can clearly see the academic publications went up and up starting 2010, and it really boomed in very recent time, like 2018, 19, and 20. Next slide, please. Similar result we can see in the Google search trend. If I look at 2004 till even 2018, people were okay with what was happening because people used to understand. We have had like linear models which people understood how they work. As and when we went ahead to use more complex models, we had to understand those models in detail, and people started searching about those trends in detail. Next slide, please. So these are different types of machine learning models, the explainability methods or interpretability methods that are there. On the left-hand side, we can see application-related explainability methods. We have model-specific or model-agnostic. So there are certain interpretability method which works for specific models, say for only for uh, particular neural network models, say CNN. There are interpretability methods which works only for CNN, or there can be model agnostic methods which can work for any machine learning model that are there. Then there are pre-intrinsic or post-hoc methods. Pre-methods are before even building the model, we can have an interpretability method in place. Intrinsic methods are embedded, so while we are training the model, we can have interpretability embedded in that, maybe through cost function, for example. And then there is a post hoc, which is essentially after we build the model, how now we can explain that model. In most of the cases, we essentially use the post hoc method, because in most of cases pre and intrinsic becomes very model specific, and we do not have much flexibility to use many models in order to understand which model works best and can give better accuracy. On the top right hand side, we have scope related. We have global machine learning interpretability method. So we have a data. We can have an interpretability method that can explain why the algorithm is taking certain decisions based on the full data. Then there is local machine learning interpretability methods, which basically tells for a particular instance, for example, for a particular customer, why it is taking certain decisions. So one is global, which can tell that, okay, a general thing, if more than 60 years of age, we cannot give a loan. That is global. Local is for a particular customer, there is a problem. So suppose a particular customer's salary and educational background is not enough to for him to become eligible for a loan, then that becomes a local machine learning interpretability methods. Finally, we have algorithm related. So there are feature importance, which essentially tells which feature is more important for a particular model's decision making process. Then there is rule based, like for example, again, age is greater than 60, and that customer is not eligible for the loan. That is more rule based method. And then there is counterfactuals. Counterfactuals are basically tells what happens if I reverse the situation, how the model is taking that decision. So for particular customer, maybe I can see that the customer is salary is less than 20,000. That is why he is being rejected for that loan. But counterfactual will tell what happens if the customer salary is greater than 50,000. How much loan now he or she is eligible for. So that kind of decisions we can get from counterfactuals, or interpretability we can get from counterfactuals. Next slide, please. Finally, there are different machine learning interpretability methods for different types of data. We have tabular data. There we can use rule-based or feature importance kind of machine learning interpretability method. So we'll mainly focus on the tabular part in the rest of the presentation. Then there are certain interpretability method for image. For example, saliency map basically tells that which pixels in a particular image is driving the decision. So which part of that image is basically telling whether an image is for cat or dog. Then there is concept attribution. For text, there is sentence highlighting. So basically which part of that sentence or which word is contributing how much for a particular prediction, and attention based, which is basically cross tab kind of thing between different words. Then there are prototypes and counterfactuals. Counterfactuals I already explained before, so I'm not getting into that. Next slide, please.
Yeah.
Okay, so that's all about the introduction. Now we'll get into the details and specific use cases of different machine learning interpretability techniques, and Aditya will basically take you through that. Thank you.
So before going back into the details, I'll just go back to this slide and talk a bit in detail about these methods. So if you focus on the first section, which is the tabular on the left hand side of the screen, you can see there are two methods, rule based and feature importance. So when you start getting into the explainability techniques and start exploring, I think the very first thing that you will stumble across will be the feature importance, which is nothing but a very simple method which tells you that let's say you have built a model with 5 different features, and which is the most important feature. And when we, in terms of theoretical, I think this is more than enough to understand how the model is performing and what the model is doing. But when we start implementing explainability into real world problems, and we start building models for actually making impact for any company or any business or any domain, then you need to know something more than the important feature. So features can be linearly related or they can be non-linearly related, right? So it can be possible that a certain age group behaves in a very different way from a very different age group. Like it may not be possible that if the age is increasing, let's say your purchase behavior is keep on increasing, or the other way, if the age is increasing, the purchase behavior can keep on decreasing. It can be possible that age 25 to 30 purchases a lot, and then age 65 to 70 again purchases a lot, but age 45 to 50 does not purchase at all. Right, so these are the kind of things that come up in the real world data and are very important for the business. So feature importance there does not do the justice. So we then move into rule-based methods, which will actually tell you these particular criteria or brackets as to where a particular model is actually performing well and the model is not performing well in a certain bracket. And then we have counterfactuals, which we will discuss in detail. So let me go into one of the methods, which is SHAP, and it is one of the very important methods that is currently doing rounds in the explainability world. It is developed by one of the Microsoft researchers, and it has its advantages across many methods, and that is why it has become so popular. So as Kushal mentioned previously about different types of methods in the taxonomy slide, so SHAP is a feature importance based method, and it is a local and a global method. So if we take the example of the bank loan application that Kushal was saying, so let's say you work for a banking company and you build a model to actually determine which customers will get the loan and which customers will not get the loan. And for one of the teams, let's say you want to understand what if a particular customer has not been given the loan. So the operations team will call you and they will ask you as to why your model is suggesting that a loan should not be given to this person, because that person will be calling back the customer care and asking them questions. So that is where the local explainability comes into play, that for every customer, I will be able to explain why the loan was not granted. But on the other hand, let's say a strategy team will try to understand that what are the factors because of which loan cannot be granted to certain customers. So there you don't need local, there you need a global explanation. So SHAP is both a local and global method which can tell you answers for both the strategy team and as well as for the operations team. The full form of SHAP is Shapely Additive Explanations. It is derived from the concept of game theory. So in the game theory, you have a concept where you want to attribute the success of the win in a particular game to the individual players. So SHAP actually does the same thing. Here, the model output is the success of the game, and different features that you use in the model output are similar to the different players. So imagine a football match and the team won the match, and you want to attribute the importance to each player. So similarly, SHAP will come into play there, and output of the match will be your model output, and the players will be individual features. So things like age, gender, previous purchase behavior, all these things become features, and we attribute importance, right? So SHAP can be implemented based on a package in Python. It's a very popular package. You can use it to actually build very intuitive visualizations on top of your model. Let me take one example of SHAP and explain as to how we use it in real world, right? So a very simple problem: what causes heart disease, right? You have certain data wherein you have age of the person, gender of the person, and historical information about the type of chest pain that they have experienced, their blood pressure, their cholesterol, their blood sugar, and different other measurements like maximum heart rate, exercise induced enigma, depression, and all those things. So based on these factors that you see, you want to predict whether a person will whether these factors result in a heart disease or not. Once you build a model for every person, you will be able to actually explain whether that person will get a heart disease or not, and that is not the end of it. So when you build models for the healthcare industry, it becomes really important to actually understand what went behind the models and how the models are performing, because doctors or researchers, they need to understand the factors, right? So we can build a simple SHAP diagnosis on top of our model, and if you see the plot on the right hand side, too many colors in the plot to actually understand it in one go, but I'll just simplify it that number of major blood vessels, if they are lesser in number, then your chances of heart disease are lower. That might not give a very intuitive understanding of the model, but that is just one of the features. So let's say we go to the third feature, maximum heart rate achieved, right? So we can see that red dots are on the right hand side and the blue dots are on the left hand side, right? So here we can safely say that if a person is having a higher heart rate that he's achieving in the history, then he is more prone to heart diseases, right? So a person whose heart rate is, let's say, 150 versus a person who's constantly getting a heart rate of 180, probably that person is more prone to getting a heart disease. So if you input these kind of features into your model and build a SHAP on top of it, you will be able to understand which features are contributing and what is the behavior of these features. So in that way, SHAP is very beneficial. It is one of the rockstar methods that is used across multiple organizations. Now, once SHAP is done, I think one of the disadvantages on SHAP is that in real world, models are not built on 10 to 20 features. They are built on 50 features, 100 features. And I have personally built models on more than 1,000 features also. So it becomes very difficult to actually manage those features. And what happens is when we build SHAP also, we try to take the top features that are there. Now, you must have heard the concept of multicollinearity that is there before model building. Now, what happens is even if we remove multicollinear features and every feature is uh, uh, independent and we feed those features into the model, uh, there is certain bit of interaction between the features that is not yet captured, right? Because these multicollinearity builds a linear model to understand the interaction between the features, and the interaction may not be linear at all, right? So these are very complex interactions that are happening between features, and we may not be able to capture them. Now, what happens is after you build SHAP, you will get to understand that if two features are very similar, uh, then there is no point of having those features in your output. And when we are making presentations of our model output, so let's say senior people, CXOs, CEOs, they don't want to have redundant information into those models. So we cannot tell them that, okay, age between this and this is the most important feature, and the next feature is whether a person is a child or an adult. So these are kind of redundant features, right? So facet, or one of the packages that is there, or the method that is there, is actually based on two different things: synergy and redundancy. So synergy is something which tells you that age derives its importance from what other feature, and redundancy will tell you that which of the features are actually redundant. So this becomes a very important tool for us to actually make our output clean and more explainable. So this is the second level of explainability that we can apply on top of SHAP, that cleans our output and makes it easy for the business people to understand. Right, so this is just one example of synergy, which is one of the synergy matrix, wherein on the left hand side you have the features, and on the bottom side you have the features on the x and y, and the diagonal is the same features, the interaction with one's itself, and let's say age has an interaction with the typical feature called LDL, so you will have a higher percentage there. Right, so this is the kind of a synergy matrix that is built on top of your SHAP to understand which features are connected with each other. And similarly, we have a redundancy matrix, wherein if the higher values of, let's say, 32 that you can see below the diagonal, which means that this feature is particularly very redundant with the other feature. So it is ideal to only show one of the features in your model and exclude the other one, because both are sharing the same information. Now, once we have completed all the other previous methods that I talked about were about the feature importance method. So feature importance only tells you a similar, very small amount of information that which features are good. And we also want to understand, as I previously mentioned, that what is the bracket in which the features are operating, or what is the value or ranges for those features. So Maggie is one of the methods that is very important and gives a lot of information in that arena. It is a global method and it can be applied to any model. And what Maggie does is that it can actually tell you that what is the bracket or the range, right? So if you look at the right hand side example, you can see that gender in female and age between 18 to 24, then the loan is granted. And similarly, if gender is in male and the income is between 3,000 to 4,000, then the loan is granted. So it is coming up with these intuitive rules. So instead of reading complex charts with, let's say, red and blue dots and a line in between and different features, Maggie is actually giving you rules which any layman can understand, even if they don't have any information about the model explainability or the machine learning techniques, right? And Maggie is a method that is available only in Java. It is currently not available in Python, and a lot of people are not even aware of these kind of rule-based methods. To give one example of Maggie, it is just created on a very simple data set. This is the Titanic data set, which is very famous on Kaggle. And you can see the output of the Maggie is a table which tells you for class 1 what is the rule, for class 0 or -1 what is the rule, and then we have metrics like precision, coverage, and RMI. So these are nothing but metrics which tell you how important is your rule or what is the coverage of this rule. So with this, imagine a data set which is very complex and we have features which are not as simple as gender and passenger class. We will be able to come up with some criteria or some brackets in simple terms that, okay, this is the feature and this is the bandwidth of the feature, and this is how you should look at the feature when taking class 1 and class 0 in consideration. So this is one of the rule-based methods. Now the other method that is of very importance is counterfactual. So counterfactual, as the term suggests, and what Kushal mentioned, is thinking in terms of counter scenarios. So let's say you are drinking a cup of coffee and you burn your tongue. So the very first thing that will come to your mind is how could I have avoided this, right? So probable answers are slip slowly or wait for the coffee to cool down. And all those things, right? So this is a scenario of thinking in terms of counterfactual, wherein you are actually trying to understand what you could have done differently to change the outcome. And on the right hand side, you can see the image also, which is doing the same thing. So the original class is loan was not given to a person, and the desired class is that loan is approved. And we are telling that increase the income of the person by $10,000. right? And if the person increases the income, your loan will be improved, and the line in between is the decision boundary. So counterfactual methods are very powerful in that scenario. There is a lot of research that has happened in counterfactuals, but the industrial application of counterfactuals is very limited. If you even go on Google, you will find just one example of loan approval. So it is kind of a task for all the data scientists out there to actually find avenues where counterfactual explanations can be used and come up with more use cases. In terms of the softwares and the library, I think a lot of implementation is available in Python. There are libraries like DICE, MOC, CEML, NICE that can be implemented straight away onto your data sets to help you understand that how tweaking a certain feature can get you a desired outcome. And this becomes very important for actionable output. So a lot of the machine learning explainability methods, people in the business world, they argue that these are not actionable. So what is happening is that they are understanding the model, but they are not able to do anything on top of it. So there is no value that is getting derived from it. So counterfactual solves that problem also, because it tells you things like increase income by 10,000. So imagine this in a scenario where we are working for an e-commerce company, and you say that a person is not buying my product. So one of the feature can be that make the person interact with a particular page. So counterfactual will tell you increase the interaction from 20 times to 40 times, and the person will start buying. So it is learning from all the different persons who are actually buying and what is their interaction, and then it is suggesting actions for a particular person to actually achieve those metric of 40 times views, and then they will also be entitled to buy. So this is very explainable or actionable for the business to actually go back and make some actions and take some actions on their business criteria itself. So that is one thing, and this is just one example of counterfactual, wherein if you see on the left hand side, there is a table which tells you that how should each feature be changed, right? You have certain features like age, gender, job, the amount, and the duration, right? So this example is just to show that counterfactual has to be worked upon a lot, and age is something that you cannot change of a person, and gender is again you cannot change. So you cannot say that, oh, go and increase your age by 5 years and we will give you the loan, right? So we need to work with features like amount and duration and jobs, right? You can actually suggest to someone to get a skilled job and they will be given a loan. So these are the kind of outputs that counterfactual gives. And the input table on the top right, you can see that the person's job was unskilled. So the output algorithm is suggesting that change the job from unskilled to skilled, and you will probably get a loan or your credit risk will decrease. So this is how counterfactual works in practice. Now, some of the these methods that I talked about, rule-based, feature importance, and counterfactuals, these are very useful for tabular data. There are certain methods that are there for the image data explainability also, because we do a lot of computer vision models, and we need to understand as to why a particular classifier was tagging a particular object as a dog or a cat. Right, so saliency based methods, gradient based methods called intgrad, gradcam, and gradcam plus plus. These are all the methods that are there to actually understand how a particular machine learning model is actually classifying an image. Now, to talk about one of the important methods, which is the class activation maps or the saliency maps. These saliency maps, they fit on top of any convolutional model. And what it does is, in the last layer of the convolutional, it tries to understand the importance of each of the pixels that are there in that last layer. And then it tries to classify those pixels. So if you can see the right hand side of the image, you can see that the baby's face is red in color, and the area surrounding that is a little hotter, which is yellow, and then all the other areas are blue in color, right? So what is happening is, to classify this image, the model is actually using the pixels of the face to actually classify that this is the image of the baby. So these pixels become important, right? So it is kind of an explainability method that comes into play, that all right, this is a baby because the model was able to identify a baby face. Similarly, if there would have been a dog or a cat, they would have highlighted, or the red area would have been around the face of the dog to understand that this is a dog, or maybe around the paws of the dog to understand that whether the dog is standing or sitting or lying down. So this is class activation map, which is nothing but trying to derive information from the last convolutional layer to understand the activations of the different pixels. There are other methods which are around the concept attribution, which actually do not work on the pixel, but they actually work on the concept, right? So let's say you have to classify a zebra into image of a zebra into, let's say you have to understand from a model whether it is a zebra or not. So it will use concepts. The model will use concepts, that is stripes of the zebra, or let's say you have to classify certain images of the doctor. So it will pick up concepts like white coat, stethoscope, or surrounding information about clinic, let's say. So these are what is called a concept attribution, wherein you are trying to pick up concepts from a particular image and classifying based on those concepts, right? So let's say you have a image of a person, right? So it will pick up concept like a long hair, and then it will try to classify into female or male, right? And that is where concept attribution comes into play for image explainability. Now, similarly, we have the same things for text explainability also, similar to saliency maps, where it was actually working on activation of the pixels. Text explainability, we have a method called line, which will try to activate different areas of the text, which are trying to classify the text into different classes, right? So here you can see that the word SQL was able to classify this particular text into whether SQL or not SQL at all, right? So this is just nothing but taking different words, treating them as features, and then activating or understanding which features are getting activated for a particular classification, and the model is able to learn from that. So it's very easy to put all of these methods on top of your actual existing. You can probably be building a neural network model on top of this, or you could be building an XGBoost model. So you can actually pick up these patterns from the models, apply these methods, and come up with some of the patterns that are important for the classification to happen. And it works in a very similar way as compared to the tabular based methods. And this is one of the methods which is using SHAP. So SHAP is a very universal method, as I mentioned. It can be used for tabular data also, and it can be used for text data also. So here it is, what it is doing is it is just classifying different words and trying to understand which of the words is actually important for making that classification, right? So very simple scenario, but different data sets and a different application. Now, once we understand these methods, right? SHAP, Maggie, Lime, and IntGrad and GradCam, and we see its application. So one of the important things that we need to understand as data scientists is the properties of these explanations, right? And let's say tomorrow you come up with a new method, or some researchers come up with a new method, and you are given the task of applying that method, right? So these are the parameters on which you should evaluate that method. You should understand that what is the accuracy of the predictions or the explanations that those methods are generating. Then you should understand the stability, right? So if you run the method more than once on a particular model, or you maybe take a sample of the data and then again run the method, so whether the generation of or the explainable generations are stable or not, you are not getting different explanations. So let's say the image of the baby, right? So first time you run it, you get saliency maps around the face. The next time you run it, maybe you're getting the saliency maps around the toys that are lying on the side, right? So you don't want to get that instability in your explanation. And then you have certain other metrics like certainty, novelty, comprehensibility. Novelty is actually one of the important factors. So I think a lot of these methods are very popular, like SHAP and Line. And if any new method is actually able to achieve the same level of accuracy or explanations, and the method is actually giving some good outputs, then we can definitely try that. So Maggie was one of the methods that we actually stumbled across, and Kushal was kind enough to suggest it to use. And what happened was we were using SHAP since a long time, and we were generating outputs on that. But when I came across this, that probably we can try some novel methods also, and we came across Maggie, and it actually changed the whole scenario for us, right? So always take into account novelty as one of the factors for exploring different methods. And just a small tip, when we as we move towards the end of the discussion, that how do you pick up interpretability methods for your model, right? So very simple things, since there are a lot of hundreds of methods that are available. When a new person starts looking into these methods, you can actually get lost there, right? So three very important questions that you can ask at yourself at that point of time is, whether you want to understand the whole logic of the model or you want to understand the reasons for a specific decision. So right, let's say we have 1,000 features, right? So you just want to understand the impact of the age on the model. You don't want to go into gender or the credit history or the income, right? So you just want to understand that. So pick up models that are actually giving you the top features and you understand that. Then there is a time limitation factor. SHAP takes a lot of time to run. Maggie takes a lot of time to run. Counterfactual will definitely take much more than SHAP and Maggie, right? So you can actually pick up SHAP and Maggie for some of your work and leave behind counterfactuals maybe for later. And then what is the expertise level of the user? So these methods again make the model simpler, but like SHAP's graph that I showed you, right, between blue dots and red dot, it becomes very difficult to read, whereas Maggie is very easier to read. So let's say you have to build an explainability method for someone who is a brand manager who does not have technical knowledge. So you will definitely pick up Maggie for them and not show them the SHAP plot. Maybe it is not beneficial for them to understand, or it will take a lot of time for them to understand, right? So these are some of the questions that you need to keep in mind while picking up explainability methods, so that you don't get lost into the hundreds and thousands of methods and are able to pick method which is most suitable. So with that, we have come to the end of the lecture. I'll keep the next 5 minutes open for any kind of questions that you might have. Thanks a lot. Kushal, any comments from you?
No, I think we can take up any questions like you mentioned.
Okay, so that was really a very wonderful session with so much and so much of details. So participants, if you have any questions to ask, please feel free to ask.
Also, I think our emails are given, and participants can reach us out on LinkedIn also. We are very active on LinkedIn, both myself and Kushal. So we'll be happy to answer questions or guide people around explainability if they need any help.
Yeah, sure, sir. Sir, then may I request you to please share the PPT so that I can send this to participants?
Yeah, definitely. I'll do that.
Yeah, then fine, sir. Thank you, sir. While sharing the recorded session, I'll share your LinkedIn profile IDs as well so that people can reach out to you. I
Sure.
think we have one. Sir, Rizwan, sir, please unmute and you can ask the question. Rizwan, sir? Okay, I think he got disconnected. Fine. Any other queries from any participants? Yeah, I should really thank both the speakers for their wonderful time, because despite the very busy schedule, because I literally know what their busy is like, it's very really too hard to catch them. So despite their very busy schedule, they took a very wonderful session and it was really so explanatory and so much information, sir. Thank you on behalf of all the participants, sir.
Thank you. And thanks, Divya, for reaching out to us and organizing these wonderful sessions throughout this week.
Thank you, sir. Thank you for that.
Thanks a lot for having us, Dr. Divya.
Thank you, sir. Again.
Thank you.
Thank
I think
you.
Rizwan sir has again joined. One second, if you don't mind.
Yeah.
Rizwan sir, yes, sir, please, you can ask. I think there's some issues with the sir side. Rizwan sir, if the chat is enabled for you, you can maybe type in the query.
Hello.
Yes, sir.
Yes, we
Hello.
can hear you.
So I would just request you to share few research papers. Okay, but only for the people who are beginners in this explainable AI, so we can start doing things. And one more thing I would like to know, sir, that is there any metrics that we can use that to which extent that model is explainable, like for evaluation of models we use accuracy, precision, recall, so these type of things are also there?
Any metrics for evaluating the power of evaluation is not there. You
Okay.
can actually evaluate the power of the explanations that are getting generated. So we don't compare the methods as such, but the explanations can be compared based on your anticipation of the results, right?
Okay.
So
And
sometimes what happens is one of the methods can give you an output, but it is not suitable to the model itself.
okay.
So that is how we compare them.
Okay, so I would just like to request the few research papers, would be base research papers. Thank you, sir.
Yeah, we'll share that.
Okay, sir. That's so kind of you to help us beyond what is required. Thank you again for that, sir.
No problem.
Thank you. Thanks, everyone.
Thanks, everyone.
Bye bye.